Welcome to lesson 19 of this Arduino C++ course, and today we're going to be looking at the L298 motor driver and how to drive small or even quite large DC motors. So moving over to the workbench, as you can see, I've got a couple of motors running already. These are the l298N boards. The motors I'm using are just these cheap tiny ones that come in a lot of the Arduino kits. However, I do have some alternate motors. We could use some of these ones that come with the robot cars, and it'll basically power any motor that you want. So that's what we're going to be looking at today, how to control these motors. As always, if you click on the link below the video, you will find yourself on the lessons resource page, and if you go right down to the bottom to lesson 19, you will find not all the resources for this lesson. Obviously there will be the sketches in here, the circuit diagrams. Click on them and you get the bigger versions. Now for today's lesson there are two circuit diagrams. The first circuit diagram is going to be used on sketches 1 to 3, and then the last one will be used on sketch 4. So let's have a quick zoom into this, because as you can see on here I have marked up some jumpers. Now let's have a look at the actual board itself. So this is a close-up of the actual board. This is an old one that I've got knocking around. As you can see, I've lost one of the screws. But the important bit that I want you to note is that there are 3 jumpers. Now, when the power comes in, we're going to be using these 2 end connections in our example. This jumper causes any voltage coming in here to be regulated to 5 volts. And these 2 jumpers are the enable pins. So they connect the 5 volt supply to an enable pin. This is for motor 1, which is, in my case, coming out of here. And obviously we've got a similar thing. So this pin here is 5 volts connected to the enable pin, allows the motor to run. Going back to the circuit diagram, I'm just going to explain this just a little bit more, just so that you understand here. We've got our motors. Now in my desktop at the moment I've got a couple of 5 volt motors, but the reason I put motor power supply rather than 5 volts is your motors could be much bigger. In fact, this board, I think it will handle up to about 35 volts. So you would have 35 volts coming in from your power supply, 12 volts if you've got 12 volt motors, in my case 5 volts because I've got 5 volt motors. And that is why when the power comes in here, if you connect this jumper, if this was 12 volts coming in, it's going to go through the voltage regulator, and therefore there will be 5 volts on these 2 pins. Otherwise, if you put the power straight in, we're going to put 12 volts or 24 volts into our logic system, and that is not going to do anything any good. You're just going to smell smoke. So the whole point of this jumper here is it changes whatever input voltage you have to a 5 volts so that these pins work correctly. Now the reason I want to highlight these jumpers is that in sketch 1, as always, we're going to do a connection test. Now, of all the problems that I had with this board, these jumpers are the biggest pain. So if suddenly one of your motors isn't working, if this left motor isn't working, make sure that this connector is seated correctly. And again, if your right motor isn't working, make sure that this jumper is seated correctly. Right, let's get on and get the first sketch running. So our first sketch, motor driver version 1, is just a simple connection test to make sure that the wiring is correct. Quite simple. Digital pin 10 is connected to IN1, 9 is to IN2, 8 to IN3, 7 to IN4. Now looking at the image, IN1 is the blue, IN2 green, IN3 yellow, IN4 is the orange. Now what these do is the ENA and ENB, they enable the left motor or the right motor. In other words, they allow power to be flowing to the motor if the appropriate pins here are set high. Now there is a grid of how this works. So the ENA, think of that as enable. If it's set high, 5 volts, and in our case we've got it permanently connected to 5 volts, the same with ENB. So we're saying both motors are enabled, they're ready to run if the controls are correct. If we have IN1 and IN2 low, motor A will be stopped. If IN1 is high, if we pass 5 volts to it, and IN2 is low, the motor will go forwards. IN1 low, IN2 high, it'll go in reverse. And if both are set high, it will stop again. So that is the control, and then the same happens with motor B. So coming down to our sketch, I've just set some constant integers. Now sometimes you'll see this as just const, just int. I tend to put const in because it actually makes the variable write protected, because pin 10 is always going to be the motor forward pin, and the motor A rev is going to be the pin 9 throughout the sketch. Set the pin modes. Obviously we're going to set them all as outputs because we're going to be sending signals. And then looking at the grid here, I'm going to set IN1 high and IN2 low. So I'm going to digital write the motor A forward high and the motor A reverse low. So motor A will spin forwards. I've done the opposite, the same for motor B. So motor B again, they will both run in a forwards direction. There's nothing else in the sketch, so let's upload that and get it running. So as you can see, both motors are running. If you've got a problem, let's imagine we just muck around with one of these jumpers. You can just hear the motor shutting down. So if you start to get a bad connection somewhere, just check those jumpers because they are a little bit fiddly. Now, the reason the motors are both running flat out is if we go back to our diagram, when we have these jumpers connected, it means that it's getting a constant 5-volt signal, which is saying whatever power is coming in, it wants a constant supply to the motor. Now in sketch 4 we'll look at how to control the speed, but in the first few sketches, whatever voltage is coming through, basically the motors are going to get that minus some losses that happen within the board. So if when you start the sketch you've got both motors running, then you know that your wiring diagram is correct. Now, one thing, if you want the motors to run in opposite directions, the way I've got this at the moment is one is spinning clockwise, one is spinning anti-clockwise, because if these motors were on their side, that would mean that I would have forward motion if I was building a car. If you swap over the pins, then obviously the motor will run in the opposite direction without you, if you like, changing the jumpers on the circuit diagram. Now within this test sketch, I just wrote how to put the motors in reverse. So if you just comment these out and comment these in, make sure I only comment in the correct lines. Now what we're going to do is, instead of it being the motor being forwards with a high and a low, it's now going to be in reverse with low and high, and again low and high again. So let's quickly upload that. And now I've got the motors spinning in the opposite direction. Success. Now, although everything's working, one of the issues I now have is that if I want to put the motor in reverse, I've got to do 2 digital writes, again for motor B. And I've got to, if you like, keep remembering what is happening within these sort of set of commands. So what we're now going to do is reduce this into a simple function so that we can sort of make life a little bit easier for ourselves, because if you've got a big project, constantly remembering which way to set these commands, it's very easy for bugs to get in, whereas if you put it into a simple function, you get it right once, it's going to be right throughout your code. So here we are, sketch 2. All the wiring is exactly the same. We've got that grid of how things work. In fact, I'm going to take a copy of that and I'm going to put it down here next to the functions that I've written. Just make sure it's commented out so it doesn't cause any issues. So you'll notice this time, if I want to send the motor A forwards, I've got a function here where I just pass a value of 1. For motor B to go in reverse, I'm going to pass it a value of 2. Now this works because I've created motor A control as a function and motor B control as a function. Now we've covered functions in previous lessons, so I'm not going to go into huge details as to how the function works, but basically we're passing a variable, an integer, and obviously if I pass a 1 I get forwards, if I pass 2 I get a reverse. There is also a default, which is any other value, and that's going to cause the motor to stop. So I'd probably pass a 0 for that. So what happens is, if I pass a value of 1, there is a switch statement. That switch statement remembers, basically how this works. So it's going to go, if I want a 1 forwards, it's going to set this line correctly. It's also going to serial print out that motor A is going to go forwards. Again, for the B, for the reverse, if I pass a 2, it's going to go motor A in reverse. And if I passed both a 0 or any other value that's not 1 or 2, it's going to set both the pins low, and that's going to cause motor A to stop. The same is true with this other function here. So basically all I've done is replace the code in the setup from the first sketch and just got it to call these two functions, one running forwards, one running in reverse. So as you can see, the function is working, both the motors are spinning in their appropriate directions, and now what we'll do is use that function as if we were building a project. So we're now going to look at sketch 3, motor driver version 3. What I've done this time is I've added some timers and a state of the motor. So if you've been following this course, we're going to use millis as a timer, not delay, because I want this code to run so that other things could happen in the background. Otherwise we're writing blocking code. Anyway, you start to see delay in the main loop, you're going to finish up with some problems. We're then going to keep an eye on, if you like, the state of the motor. Again, we've done this in previous lessons if you're following the course. Right, in the setup, all we're going to do is start the serial monitor and set the pin modes for the various pins. Coming down to the main loop, current millis is back for those following the course. That's going to keep the current board time, and then what it's going to do is, just as we've done with other timer circuits, if current millis minus motor millis is greater or equal to the timer, it's going to set motor A millis to current millis. And then what it's going to do is check the state of the motor. So if the state of the motor is greater than 0, and that is the value that we are going to pass to that function, motor A control. So if it's greater than 0, that means the motor is running forwards or backwards. We're going to tell it to set motor A state to 0 to stop the motor. Now the reason for this is we're going to call random directions, and what I really didn't want is the motor running forwards and then just sticking the power in reverse. Probably not the best thing to do for the motor. They're cheap motors, so I'll try and make them last as long as possible. And then what I'm going to do is set the timer for 1 second, so allow enough time for the motor to stop, and then it'll come round and it'll change the direction again. If the motor is stopped, so if the motor state is 0, so it's not greater than 0, it's just set to 0, then all it's going to do is pick a random direction. Now you'll notice random, we have a value 1 and 3. Now the variables that we pass to the function for setting the direction, if you remember, is 1 or 2. So what happens with the random function? It will pick a value between the first value that you set and the value below the last value. So if you set 3, then it's going to pick values 1 or 2. If I'd set 4, it would be 1, 2, 3. It would pick a value between them. The other thing I'm going to do is then get it to pick a random time between 3 seconds and 10 seconds to run the motor in that direction. That then gets repeated for motor B. So motor A and motor B will be running in random directions for random periods of time. Now the point of doing this is it just saves on putting some buttons in, but it allows you to sort of get the hang of using this function, because if we were to add buttons or various other things to control the motors, it would be calling this function. All we're doing is skipping the buttons for now and going straight to the control command. So as you can see, both motors are spinning, and now and again they are stopping and then choosing a new direction. So if we put this alongside the code, we can now see the serial monitor going, and we can see which motor is being stopped, started, and the direction it is being sent in. As you can see, sometimes they're stopping together, the rest of the time they're stopping and restarting individually. So at this point we have a successful function for controlling the direction of the motor, or for turning the motor off. Now let's have a look at how to control the speed of the motors. Now to control the speed, we're going to use a thing called pulse width modulation. Now if we look at the current way that we are controlling the motors, here is a very, very basic diagram. We've got ground and 5 volts. And what we're doing is when the motor is stopped, we are sending nothing. When we send the pins high, we will send full power to the motor, in my case 5 volts, and that will drive the motor along. Now what I have done is reloaded sketch 1. And sketch 1, if you remember, just sets the motors in a direction. They're now currently set in reverse. And we'll look at the webcam and we're going to play a little trick to see if we can change the speed of the motors. So as you can see, both motors are currently running flat out. Now what I'm going to do is try and slow them down. And I'm going to do that by trying to play with the power. Now, as you can see, if I get this just right, I can sort of slow the motor down by pulsing the power on and off. And that is basically what pulse width modulation does, except of course it does it much better than I can do by pressing the button. So let's have a look at how pulse width modulation, or PWM for short, works. We start off by going to the reference, and we're going to look at a function called analog write. Now, analog read is the function that you use for reading pins A0 to A5. Analog write is very different because it works on digital pins. And if we look at the Uno, we can see that the PWM pins that we can use are pins 3, 5, 6, 9, 10, and 11. Now, if you read down through the various bits of information below, you will find that there are certain pins that are better to use than others. And the pins that are best for us in our project, I think it's pins 5 and 6 somewhere that it tells you there is an issue. There we are. Notes and warnings on pins 5 and 6. There can be issues if you're using millis or delay. Now, any project that I would be writing would have millis within it, so it's best to avoid, for my projects, pins 5 and 6. If we think about the project that we're working on, we're already using pins 10 and 9. We don't want to use 5 and 6, so the pins that we are going to use are pins 3 and 11. Now, scrolling down through the reference, there is actually some more information at the bottom on PWM. So let's click on that reference. This is how pulse width modulation works. Now, the frequency is 500 Hertz. So 1 Hertz is 1 cycle per second. So 500 Hertz means this is happening 500 times a second. So that's sort of, what's that, 2 milliseconds for this to happen. Now, this is how pulse width modulation works. So before, if we either had 0 for off or 5 volts for on, if we set the duty cycle, so the way this works is you can set a value between 0 and 255. If we set the value at 255, that means it's always going to be on. So for that 0.2 of a second, it's constantly going to be on, and then the next 0.2 of a second, it will be on again. If we set the value to 0, then it will be off for the whole time. If we set a value to 25%, which is a value of 64, you can see that the 5 volts is on for 25%, then off, then on, then off, on, off. So if you like, it's a bit like me trying to press the button, just nudging the button on. So if you like, it's getting 5 volts for a very small period of time, then there's no power. If we set it to a 50% cycle, then obviously 5 volts for half the time, 0 volts for the rest of the time. So that is how pulse width modulation works. You're basically sending endless pulses rather than a constant voltage. Now, PWM is very good for DC motors. If you start to use, just reduce the voltage, you tend to lose certainly some starting torque on the motor. Keeping the 5 volts can allow you to control the speed but still have some starting torque, which is quite important when you are working with motors. Now, before we can, if you like, change the code, the first thing we have to do is change the circuit. Now, if you remember those jumpers here, they have both been removed. So before, the power was constant. Now what we're going to do is through pins 11 and 3, which is the ones that Analog Write suggested that we use. We're going to be turning the power on and off. We're going to be supplying this sort of 5 volts, turning it on and off very quickly, the same with this pin here. So we no longer need that constant 5 volt supply. So just connect up pins 11 and 3 to ENA and ENB. So once you've built the circuit, taken those jumpers off and put those 2 connections across, we come to our final sketch, motor driver version 4. So pin 11 is the PWM for motor A, pin 3 PWM for motor B. I have set this in my list of pins, so constant int motor A PWM and motor B PWM. Now, one thing that's odd about using Analog Write, you do not need to set a pin mode. It's quite unusual, but pin mode is not required. So let's have a look at the code. Now, originally in Sketch 2, we set motor A control to 1. That sent motor A forwards. Motor B control set to 2 sends it in reverse. The only difference now is we're going to keep those functions in. They're still in the bottom of the sketch. But we're now going to combine the direction control and then use Analog Write for the speed control. Now what I'm going to do to show you an example of this is we're going to set motor A PWM to 90 and motor B PWM to 255. Now 255 is the maximum speed, 90 is sort of a much lower speed. So let's get this sketch uploaded. So as you can see, the both motors are now spinning, but obviously the motor A, this one over here, that's getting a value of 90 sent to it, is running much slower than this one, which is running at its original speed of flat out. Now, one thing to be aware of with PWM, what I've done here, if you look on the camera, I've now got the left motor spinning flat out, and I've set the speed of the right motor to 70. Now, although it says that the speed is between 0 and 255, that is not quite true. If we come back to our PWM diagram, let's just move that across so we can see, there comes a point where the, if you like, the kick, the 5 volt kick, is so infrequent that it is not enough for the motor to move. Now I'm going to show you that if we just bring up the sketch again. At the moment I have it set at 70. What I'm going to do is turn the power off, and now I'm going to turn the power on as if I was asking those motors to start with a command signal. Now at the moment they're both working fine, but you'll notice if you look at the right hand motor, it does take some time. There it goes. Now and again there's so little power that it struggles to actually start. It is moving and eventually it will get there. But this is an issue that you will have with your motors. So basically, if you're doing a motor project, you are going to have to work out at what speed, what PWM frequency your motor can actually turn. Because obviously, these motors that I'm using have got no load on them. If this was controlling a model car or something like that, then this start value may have to be at about 120, maybe even up to 150. So right now from today's lesson, we have now got direction control and we've got some speed control using PWM. Now what we'll do in the next lesson is look at how we can use the functions and that we have, if you like, developed today, and control them either with some buttons or with something like a joystick, as if we were controlling a vehicle of some type. So I'm going to end the lesson there to try and prevent it from becoming too long. And as I said, in the next lesson, we'll use some control inputs to control the motors and the direction and the speed using something else. So I hope this has been useful to you, and I'll see you in the next lesson. Bye for now.